Apologies for the technical issues there. I thought it might have been just me, but even when Stephen DeCandy or Owen couldn't fix it, I figured, oh, well, that's all right. So for those of you who don't know me, my name's Warren Reid from the Defence Science Technology Group. Effectively, we're down the Fisherman's Bend side, 4K down Lorimer Street here. And I guess what I'd like to do today, and I suppose I could have gone on for an awful long time, but considering it's a winter solstice, I didn't want to go on too long tonight. But what I hope to do is just give you, I guess, an overview of the, in particular, the underwater shock loading area, how it applies to naval platforms. And as part of that, I guess what I was going to try and do is cover some aspects of what we call equipment vulnerability, structural vulnerability of naval platforms, and then I'll finish up with, I guess, probably the last 10 or 15 minutes looking at whole platform shock testing to explain what that's all about. Okay, so I guess a bit of corporate advertising here first, but from Maritime Division of the Defence Science and Technology Group. So as I said, we have sites at Fisherman's Bend just down the road here, also at Edinburgh, South Australia, HMA Stirling over in WA, up in Sydney, also smaller sites up in Queensland, probably test sites and so forth, about 2,100 people, I think, something of that order. But in Maritime Division, I guess we have what we call 6 major science technology capabilities. So I'm part of the Maritime Platform Performance, MSTC, the team that looks after. We also have at Fisherman's Bend acoustic signature management, MSTC, non-acoustic signature management, MSTC, and then in Sydney we have a Maritime Autonomy Cell, or MSTC I should say, and then spread across Edinburgh, South Australia, and also HMA Stirling, Perth. We have 2 other MSTCs looking after sea command and control, and also sonar technology and systems. Okay, so I just want to talk to you about tonight is shock loading of naval platforms, and I guess this is effectively a subset of what we call an area called platform survivability. And I guess the easiest way of explaining this is that what we have here is our survivability onion, and to explain that in a little bit more detail, I guess from the survivability perspective, if you think of the layers of the onion, since survivability, I guess maritime warfighters try not to be fired at generally. So the outer layers of the onion here represent not being seen out there, for instance. As you begin to move into the centre of the onion, if you are seen, you try not to be targeted. If you are targeted, you try and avoid a hit from a weapon that might occur. But ultimately, I guess what I'm going to be talking about tonight is if you are targeted and the weapon does hit you, what we can do or what we have done to try and protect those naval platforms once they're hit by a weapon. And effectively, you survive, I guess you can divide these areas up into what we call susceptibility, so try not to be detected, vulnerability, and that's the area I'll be talking about tonight, so what is a vulnerability of the platform if it does get hit. And there's also an area called recoverability, so after you have been hit, how can you recover the platform, or how well can you recover the platform and try and get back onto your mission. So the group I look after is what's called Dynamic Military Loads Group, and I get asked by a lot of people, was that something about moving logistics or moving defence equipment around the nation? But effectively for us it's looking at the immediate structural equipment systems damage from a weapon attack, and we do all this work in support of the Navy, trying to give them a much greater confidence in the survivability of their particular platforms. And in that particular area, I guess I've touched on this a little bit, I guess the 4 areas that we consider the work we do for the Navy is looking at the structural vulnerability of platforms, so how a structure would respond to a dynamic weapon loading. Obviously on naval platforms, a lot of equipment on those ships, so there's aspects of equipment vulnerability or survivability of that equipment on board the platform. We also do a little bit occasionally on human vulnerability. I guess the performance of the systems is only as good as the performance of the humans on board. So if the humans are damaged, for want of a better word, then they can't operate those systems. And we also look at aspects of the requirements or the shock standards as it applies to Navy platforms I guess there is a requirement on a lot of our platforms in terms of they want a certain performance of that platform, in this case in an underwater shock loading environment. Okay, so what is an underwater explosion? And whether it's an explosive that detonates in air or underwater, it's the same, basically the same physics, how we get different behaviours of an explosive underwater. So if you imagine a explosive charge detonating, we usually use a detonator, a DST, we actually use a special type of detonator, very high voltage detonator to detonate explosives. But when you detonate an explosive, you get a very high speed burning of that explosive, typically in the thousands of metres per second. So that burn moves through the explosive charge, and then when it gets to the outer perimeter of that explosive charge, that shock wave forms, also enters the medium, whether that be air or water. Now also, so it's the same thing that happens in air, but in air, for instance, that shock wave moves around about 300 metres per second. Underwater, it moves about 1,500 metres per second underwater. And I guess the velocity of propagation is proportional to the density of the medium. So if that shock wave, for instance, entered a steel ship, then that shock wave will move through the steel components of that ship about 5,000 metres per second, thereabouts. So there's a shock wave form, but there's also explosive products for it. In air, those explosive products will just dissipate in the atmosphere. Underwater, they actually do something completely different. So, for instance, typically what happens, so looking at a shock wave, I guess just describing that for the start, we get a very rapid rise to a peak pressure and then a slow decay from that shock wave. And in terms of the peak pressure you get, that can be in orders of megapascals, so huge pressures from explosive charges. The explosive products that I mentioned, so if this is our shock wave forms, what actually happens in explosive detonation products underwater is that they form a gas bubble, and it's a rapidly pulsating gas bubble. So you can imagine very high temperatures and very high pressures, and that gas bubble, it rapidly expands and it goes past the hydrostatic pressure in the water, and then it contracts again. So you can actually get about 3 or 4 pulsations out of this gas bubble underwater. And in fact, if you look at the shock wave and the gas bubble that forms, there's about 50% of the energy in the shock wave and about 50% in that gas bubble underwater. And the thing about the gas bubble is that as it expands and contracts rapidly underwater, it tends to migrate towards the water surface. So this is especially important, for instance, if you have a naval platform nearby. And if that gas bubble is close enough to the platform, actually it can collapse onto the hull of that platform and do quite considerable damage. I should also point out that there's quite a range of different explosives. A lot of explosives are purely generally made for air blast, but generally for underwater explosives there are different formulations. And what actually happens when you change the formulation of an underwater explosive is that they're trying to change the performance of usually the shock wave, but often the performance is gas bubble. And for an underwater explosive, for instance, what they'll do is to add aluminium to the explosive charge. That slows down the burn rate of the explosive charge and actually slows down the bubble oscillation of that gas bubble. And in that situation, the reason they do that is most naval ships, maybe 120, 140 metres long, have a natural hull girder frequency of about 2 hertz. So what they're actually trying to do is change the natural frequency of this pulsating gas bubble to about 2 hertz. That's where you pick up resonant frequencies in the hull girder, and for a close-in weapon, that's where you actually get a lot of damage to a ship hull by hogging and sagging and breaking the back of the ship. But I'll show you some of that shortly. Okay, so that's the explosive side of things, what happens underwater. What are the typical damage mechanisms we get to a platform in this situation? So I've mentioned the shock wave. That shock wave propagates through the water when it finds a structure nearby. That shock wave will get transmitted through the structure, through the hull plating, through the bulkheads, etc., up through the main deck, through the rest of the platform. If the explosive charge is far enough away from the platform, it generally won't do any structural damage, but it can do quite significant equipment damage, and that's due to the very high accelerations that shock wave transmits to the structure of the platform. If that explosive charge is much closer to the platform, what we find, you also get shockwave loading, and I guess in this particular situation you get quite extensive hull plating damage. But what you find is that that gas bubble I mentioned before, as it expands and contracts, the resonant frequency of the gas bubble excites the natural frequency of the hull girder, and you get braking at the back of the platform. I'll show you this in the video shortly. With the bubble, after it's hogged and sagged the ship, that gas bubble, if it's close enough, can actually collapse in on itself and form a water jet up through the ship. And the next video I've got, hopefully this is going to work, fingers crossed. So this was a video from about 1999. So HMAS Collins, first Collins class submarine, fired its first heavyweight Mark 48 torpedo in Enga. And the unlucky recipient of this was the ex-HMAS Torrens. Now I should point out Mark 48 torpedo is about over 300 kilos of explosive. It's actually designed to sink cruisers, maybe about 4 times the tonnage of Derwent. So what you're about to see here is, I guess, quite significant devastation, but it's a great video to show all these different mechanisms. But then I tell people it's actually a lousy video to show because this is not what typically happens. When a certainly for a small ship, but in the real world, for instance, there's only been 3 torpedoes fired in Angus since World War II. So one was in the Falklands, the Belgrano, Argentinian vessel. One was, I can't remember, it was the Pakistans or the Indians. One fired one of the other and took out one of their corvettes. And then recently, or allegedly, the North Koreans may have fired a torpedo at one of the South Korean corvettes. I think it was about 2006. But when I talk about underwater shock loading, there's been hundreds and hundreds of mining incidents since World War II. So when you see a torpedo hit, you think, oh, there's not much you can do about this platform, but a lot of what we do applies to mining incidents applying to naval platforms. So when I show this video, what you'll see, and I can stop in various spots, you'll see the shockwave loading. You'll see actually a white cavitation zone around the platform, and that's because the compressive shock wave that forms reflects off this air-water interface, reflects as a tensile wave. The water can't stand tension, and therefore the water cavitates. So you see a cavitation zone. You'll see the ship hog up initially, and that's due to that big gas bubble expanding. You'll see it then sag as the gas bubble contracts, and then you'll see the gas bubble collapse in on the underside of the ship and jet up through the structure. So fingers crossed. Okay, we'll move on. So in the rest of this presentation, what I mainly like to concentrate on is just the shock loading part of these mechanisms. Acting on a platform, there's a lot of information around what I could go into for the bubble collapse, but I'll just cover the shock loading side of things. So what actually happens when that shock wave interacts with the structure of the ship is that it reaches the whole structure of the ship at about 1500 metres per second. That shock wave is then transmitted through the structure of the ship. And if you look at the response of the platform in this particular location, doing a velocity versus time plot, you'll see a very sharp rise in time when a change in velocity as that shock wave interacts with the ship. And that's then followed by, after the shock loading stops, we then get a gradual decay, or as the ship settles back down again after shock loading. But as you move up through the ship's structure, so for instance up to the main deck, and other areas there, you'll find there's a similar velocity response but a drop off in acceleration. And by the time you get up to the superstructure, you find that the acceleration drops off quite dramatically. And what this means is if you have equipment down low in the ship, very susceptible to failure due to shock loading, whereas that equipment up in the superstructure is likely to survive that same type of loading. So accelerations drop by an order of magnitude at least as you move up through the structure. One of the things that does happen though is that very high accelerations, low displacements on the structure. As you move up to the top levels of the ship, you get very big displacements and high accelerations. And that can actually cause other problems for equipment that's in those locations. So just to show that a little bit more, so if we have an explosive charge a long way from a platform detonating at that large distances, you begin to get temporary disabling of equipment. Your mission capability of the platform may be degraded a little bit. Usually you get all those systems up and running again. Moving in a little bit closer, what you find is that you may need some shipyard assistance after there's been a shock load on the platform, especially for instance non-hardened equipment such as commercial off-the-shelf equipment may have failed. Moving in closer again, you'll find that you'll get hardened systems and possibly human systems beginning to fail. And for humans, if they're standing, for instance, it could be breaking of ankles and kneecaps and that sort of thing. In fact, the safest position for a human is up on the superstructure, maybe on a gas strut chair or something like that. And then finally, if the video of torrents had worked, you begin to get serious hull damage. And like you saw with torrents there. And in that case, in torrents, you saw the bubble doing a lot of damage to the platform, but there would have also, shock weight would have also caved in the underside of the platform in that situation. Okay, so what do we do to try and protect Navy vessels a little bit more? So I've indicated generally the hull is a lot more shock resistant than the equipment. However, you can, with those closer loadings, you can get significant hull plating or structural damage. With the equipment and systems, if they're critical, for instance, to the float, move and fight parts platform, so navigation, propulsion, combat systems, etc., that equipment will often go through a shock hardening process, and I'll show a little bit more of that shortly. And I guess one of the important things is equipment that's gone through a shock hardening process generally goes in a laboratory shock test machine, but there's no guarantee that equipment will survive the same shock loading on a ship. So one of the things we do, and I'll cover more of this, is to try to do what we call a full-scale ship shock trial. And that's where you take that platform, blue water, detonate a large explosive charge next to it, hopefully everything survives, and you can sail back and forth. And I've also mentioned, these days there's a move to put a lot more commercial off-the-shelf equipment on platforms rather than going through a shock hardening process. And you can get that equipment survive by using resilient mounting, shock mounts. One of the problems using shock mounts is that big displacements can cause equipment to hit each other and take each other out that way. Okay, just briefly, Australia has a shock standard for the Royal Australian Navy in terms of the response or the survivability we expect out of our platforms in terms of equipment and structure. Prior to about the mid-90s, we actually didn't have one. We actually relied on, overseas designs and the shock standards that came with them. What actually highlighted some of the issues, the fact that we didn't have a shock standard, was that our Collins-class submarines was a Swedish hull with a US combat system, and no one knew how that related to each other, whether the Swedish hull would survive a higher level than the US combat system. So as a result of that, we ended up trying to produce our own shock standard. In fact, that's now been utilised in various acquisition platforms that's happened over the last few years. Okay, so in terms of shock hardening equipment, we generally aim to reproduce the same sort of shock environment on board a naval platform. The first three of these testing techniques here, floating shock platform, medium-weight shock machine, and lightweight shock test machine, are pretty common throughout the world. These are standard US shock testing machines. Basically, for each of these machines, depending on the mass of equipment put on there, for instance, the floating shock platform can take masses up to about 28 tonnes. Medium-weight shock machine, I think it's about 1.5, 2 tonnes, and the lightweight shock machine is just for small items of equipment. This is a picture of a medium-weight shock machine here. Quite simple. Basically, it's just a mechanical shock loading machine where you have an ample table here, and in this case, with a radar set up on there. And basically, there's a huge hammer, a 1-ton hammer that swings through an arc and just comes up underneath that platform and gives it a mechanical shock load. And I guess that's more of a US and a little bit of UK philosophy. You find if you look at equipment tested European specification, they tend to use more drop towers, electromagnetic shakers and other types of specialist equipment. I did have a video of a floating shock platform being shock loaded here, but you would have seen a big splash, heard a big bang, everything shake. And I'm afraid that's about all. Actually, I'll try and see what happens. This video is a lot smaller. I'm not. That's probably off. If the other one didn't play, I suppose. So. Oh, okay. This one is going to play. So, explosive underneath here. It's about 20 kilos of explosive. One of the things I was going to say, if you listen carefully, you'll hear the explosive detonation, but you also hear the bubble pulses, and you see the bubble pulses as it affects the platform. You see the platform give another couple of jumps. In fact, I'll play it again just to... So if you listen very carefully after the detonation, you'll hear the bubble pulses. And you see the platform jump again a couple of times. But that's a much longer duration loading from those bubble pulses, but it can do an awful lot of damage, especially for instance, low frequency response equipment, like engines on shock mounts. Okay, just to cover, we don't generally do a lot of work in the equipment vulnerability side of things, but just to give you one example of some of the work that we've done in the past, we did have an explosive test facility at Epping, about half an hour's drive from here. That's since been eaten up by the local commercial encroachment in various buildings nearby, but we do have a new facility we're developing about an hour and a half's drive from Melbourne here up near Dagambie, a much bigger facility and potentially a much more useful facility. But as an example of some of the work we do in the equipment vulnerability side of things, Collins class submarine has about 150 hull penetrations, doing various things, and a lot of those are for taking cooling water in and out of the platform. One of the biggest problems with shock loading is if you get a major failure of those hull penetrations, the valve behind it, you'll get immediate and catastrophic flooding of the submarine. So I guess the hull valves tend to be considered to be fairly important. One issue we were worried about with the Collins class hull valves is that they do corrode and they can replace them every 3 years. So the concern was what happens if we get a shock loading and you've got a corroded hull valve. So, for instance, some of the tests we've typically done is to have some full thickness sections of hull plating with a number of valves mounted in them, and we can put an explosive charge above that, lower it underwater, and actually load the valves up to their full design level that they're expected to survive. And I guess the outcomes of that test was that those corroded hull valves did survive at full design level. So one of the things that came out of this work, for instance, was that rather than replacing those hull valves every 3 years, they actually replace them every 5 years. And to replace all those valves costs many millions of dollars. So again, there's something we would contribute to the, saving the Navy a lot of money in that situation. Okay, that was equipment vulnerability. I'd like to just quickly give you an overview of some of the work we do in the structural vulnerability area. It became apparent to us a few years ago that we get asked to comment on the various naval acquisitions that are out there and the technical aspects of those naval acquisitions. One thing we realised though is when we've commented, for instance, in the past on the structural vulnerability of those platforms, in terms of, for instance, the steels they're made from, that we didn't have a real means of quantifying the performance of that steel in terms of the overall platform vulnerability. So, for instance, one steel compared with another, we'd like to say, well, this one has a vulnerability improvement of, say, 10%. We didn't really have a process we could go through for that. So one of our current work programs is looking exactly at that. And this is just, I guess, a roadmap or a narrative of what we're doing here. So we have a lot of experience in the dynamic loads or shockwave loads physics area. We've also got people on site with a lot of experience in materials properties, performance of materials at high strain rates. And I should point out that compared with quasi-static strain rates and explosive loading, you can get about strain rates of 10 to the 4 or 10 to the 5 per second. And at those loading rates, the properties of those materials can change quite dramatically in terms of their ultimate tensile strength, yield strength, and so forth. So with that information and some of our vulnerability code, we'll talk a little bit more about this next slide. That all comes together and we can do a vulnerability prediction of the performance of a platform. And then in combination with our regulatory requirements, shock standards, and our vulnerability assessment, we get an even comments made about the platform's viability and also the platform capability, for instance, after it may have been shock loaded. And just to indicate some of that work, so the work we're doing at the moment, for instance, might be looking at the performance of different types of steels, might be future platforms. And I guess the work we're doing is looking at a combination of the microstructural modelling of those steels. So at the moment, if you want to find out the mechanical properties of those steels, you need to do a lot of testing. We're hoping we can go to using various software to model the performance of those steels from looking at the microstructure. High strain rate properties of materials. We've done a lot of work with Normetall in Germany in terms of giving those steel samples. They do high strain rate testing of those steels, well, relatively high strain rate testing. And I was going to say we do some high strain rate testing. But also there's been a combination of experimental testing, such as using explosive bulge tests, which I've got a few slides on that. And that all comes, those three areas come together in our structural vulnerability model, which I'll show a little bit more. But just to talk about some of the, I guess, the high strain rate testing, material testing. For those who haven't heard this before, we utilise what we call a standard explosive bulge test, and basically we have a big steel die block, about 750 millimetres square, and about, could be up to 300 or more millimetres deep. You place on top of that die block a steel plate, typical section ship hull plating, and then above that we detonate an explosive charge at certain standoff. And typically what happens is that plate can go, we test a range of temperatures, and what we're looking for there is a ductile brittle transition temperature of that steel plate. And the more energy you can absorb at a lower temperature basically means that that material is much tougher in terms of its fracture toughness. And ideally that's the sort of steel you want in this situation when you're getting explosive loading platforms. We've also worked on a variation of this test in terms of changing the explosive charge size, moving different distance away, and that's been part of our high strain rate explosive testing. And from that we're trying to get the specimens to deform at different rates, and then different rates, and then trying to capture that information with sensors. And I think, the next slide, this video may or may not work, but just to show, this is a section of hull plating here, sitting on top of the die block. This is the explosive charge sitting on that arrangement. There's a cardboard box around the steel plate. Probably in this situation, that steel plate was cooled down, maybe minus 20 degrees, something like that, to keep retain the hot plate. But it's also stands the explosive charge off away from the steel plate. You can do a number of these tests at one time, and hopefully, if the video's going, I made myself here. This is high-speed video showing an explosive bulge test. But what we're trying to do here is capture, we've got sensors on the plate trying to capture the loading situation and so forth, and look at the performance of that plate. So, fingers crossed. So, I mean, what you saw was obviously in slow motion, but from start to finish of that is only about a couple of milliseconds. I won't try and step through it. I was going to show that you can see the fireball interacting with the plate, and shockwave will also interact with that plate. Without the mounting, it's going to be a little bit hard to get that up and running. So just to show you some of those results, so for instance, the DH36 steel versus the EH36 steel, Basically that's 360 megapascal yield, typical ship hull plating steel, the DH1. In one of those explosive bulge tests where they crack or weld, crack a rest starting here, so as those plates deform, the DH grade, which I guess is a lesser grade than the EH grade, begins to split, but the EH grade steel stays intact. And I guess in this work program, what we're trying to do is to build up the ability to quantify the performance difference between these two steels if you made one platform out of D grade steel and another platform out of E grade steel, for instance. Hopefully you can say, well, there's a 15% improvement in the performance of the vulnerability performance of that platform. Let's just show some of the modelling we've been doing of this particular explosive bulge test. There's no video information of that. Okay, just very quickly, some of the structural vulnerability prediction techniques that we have available to us. Our traditional techniques, usually empirical based codes, so we've done a lot of testing in the past, looked at the performance of various scale and non-scale structures. We also have been doing a lot of work lately on fully coupled physics-based codes, such as, for instance, LS Dyna. And whereas the empirical-based codes can run straight away, you get an answer straight away, I guess one of the issues is if you change the structure of the platform and move to a different platform, you need to reconfigure those algorithms to match that particular platform. One of the advantages with LS Dyna and physics-based code, so for instance, in this case, this is a hull valve, submarine hull plating. You can model that in detail in terms of the shock wave moving through the platform, the response of that hull valve and so forth. The only problem, of course, is that whereas this might run straight away, this scenario might take 3 or 4 days to run, only looking at about 10, 15 milliseconds. What we're looking at is somewhere in between these two codes in the future where, for instance, we have access to a semi-empirical FE code, tried, whereas in this case, if you want to model the whole platform, it would probably take a couple of years to run, but we've tried, I guess it's halfway between the fully coupled physics code and the very empirical basic things, and it might take, for instance, a few hours to run a full ship structural evaluation. Okay, just the last bit I wanted to cover, and probably gone on too long already, but how do we prove to the Navy that their platforms will survive a real shock loading scenario? Typically what has been done in the past is do a full-scale shock trial. So this is basically taking that platform out into blue water, typically off the continental shelf around Australia, and detonating a large explosive charge. The US has done this a lot in the past, we've done a little bit in the past, but one of the major problems is a hugely expensive way of doing it. You tie up the business crew, the platform, trials personnel, huge logistics. Imagine getting that platform out there, getting the explosive charge out there deployed, you've got support ships and everything else. And for instance, the US test, they spent up to about $30 million, and that includes also the panel beating of the platform afterwards, knocking some of the dams back in. But probably one of the biggest disadvantages of this is environmental considerations. As you can imagine, I think it was about 25 years ago, the US tested one of their aircraft carriers, they detonated 20-tonne explosive charge next to it. And the reason they do such a large explosive charge is they want a linear shock wave getting to the platform and loading every single bit of the structure and every single bit of equipment. As you can imagine, that's probably not great for the environment, especially if you've got migrating whales or dolphins or whatever else around. So there are some pretty major environmental considerations. In fact, you probably need to keep an area clear of about a couple of kilometres around the platform when you're doing those tests. Aeroplanes in the air looking for mammals, various boats in the water doing the same thing. However, what the one big advantage of these types of trials is that it does prove and verify that there's a complete system. So you may have tested that equipment in a laboratory shock testing environment. You put it on the platform, it may still fail simply because of its weight, it's where it's installed and how it's installed, and whether the contractor has done everything properly. It does prove and verify the structural response to the platform, and one of the things we get out of these tests is you get a structural response out of that platform to an explosive charge. And you can use that information, for instance, at a midlife refit to calculate how that platform is likely to affect the equipment on board. I think that's one of the other major things it does identify problems for rectification. applications. That's why we try and do the first platform series. And hopefully you don't find anything wrong, but usually you do find a couple of major things wrong, and they'll try and fix the issue for the remainder of the ships that are built in Mars. Now, I've got here a little bit of video. So the last shot trial we did here in Australia was HMAS Franklin in 2003, a Conquest submarine. And I'm going to get the fingers crossed that this is playing. So the submarine was submerged about 20 metres down. If you look at the shots, the shot rate, the platform will also get double places. Okay, and basically, Collins did pretty well on that shock test. We ticked the box in terms of its surviving the shock loading. However, I guess we didn't detonate anywhere near as large explosive charge as the US did. But there's still major environmental considerations in that trial, and it's unlikely we'll be able to do another trial like that here in Australia. So what are the alternatives? You can rely upon some of your experience in terms of determining how equipment fails. If you've got new equipment on board those platforms, you may or may not be able to predict whether it's going to fail. You can do scale experiments, various numerical modelling. I think a lot of people hope to do numerical modelling and simulation platforms in the future and not have to do any shock testing. But there are alternative methods. And just for the last few slides here, what I just would like to cover some of those alternatives that we're considering here in Australia. And one of those is seismic air guns. For those who don't know, seismic air guns are used in the oil and gas exploration industry. I guess they're about the size of a 9 kilo barbecue gas cylinder, but they weigh about 100 kilos, very thick-walled stainless steel. Basically just an air storage container, and you can fire them electrically to release that air out into the water. But basically when they're used in the oil and gas exploration industry, they'll tow about 50 of these things behind the ship. They'll fire them, bring them away, look at their acoustic source, they'll look at that acoustic signal, how it bounces off the seabed, and from that you can assess whether there's oil and gas down there. Anyway, very reliable. You can fire these things probably 20,000 times a day, and they're an off-the-shelf item. So what are the advantages potentially of using an air gun? There's no explosives handling or misfire problems. If you have an explosive misfire, you've actually got to stand back for at least a couple of hours to make sure that explosive is not burning away underwater or other issues that may have happened. So consequently, there's low risk to the ship's crew, trials team, and also, of course, maybe divers, I suppose. And also from the environment. I'll cover more of that shortly. Very repeatable in terms of the pressure pulse they put out and the loading they put on the platform. And as an example, cost-wise, Australian test, HMAS Franklin costs about $5 million to perform. We're estimating that same test with air guns would be about $1.5 million. And I guess one of the big savings of the logistics side of things is that you no longer have to take that platform out of the blue water, leave it tied up alongside the port, and then just fire the air guns against that platform. May or may not need the crew on board, take away all the requirements for support vessels, etc. And I guess most importantly, rather than explosive residue in the water, you've only got compressed air. And I guess the other important factor is you probably only need to have a very small mammal exclusion zone around that platform rather than a couple of kilometres actually with explosive charge. And just to show you a couple of air guns firing. So these are just a couple of standard air guns. This is in the configuration they have when they're using an oil and gas exploration. But you'll actually see similar behaviour as what you see in an explosive. You see that, you won't see the pressure pulse, but you see you see the gas suddenly into the water, bubbles come together and you just get that pulsation effect as you would with an explosive charge. Okay, environmentally much easier to do. However, there still is a requirement to have an exclusion zone around these guns. I've got 100 metres radius, so it should actually be 100 metres diameter. But around the platform, you probably only need an exclusion zone of about 50 metres. And leave the platform. But we will have to, if we do one of these tests, we will have to go through the environmental requirements and making sure that we're not going to harm any passing dolphins, etc. Okay, the big disadvantage with air guns is that explosives, you can have them 100 metres away from a platform, and you get a quite significant shock loading. For instance, with air guns, you'll have to have them right up against the hull of the platform because the pressure profile of that platform is significantly smaller than explosive charge. And just to show you how we might do an air gun shock trial. For instance, so what we have here, this is a large float, which we have an air gun module hanging off. There's a number of air guns down here. And basically, you bring this module and float it up to the side of the ship, and then just fire the air guns, electric air guns. And this is one of these modules here, sorry, 4 of them here, next to each other, and they've got 16 air guns that you bring up against the side of the ship. One disadvantage with this is that you've now got point loads acting on the structure of the ship. So there is a danger that you can do localised structural damage. So that's one of the aspects we've been looking at over the last few years as to how far to stand them off, how much pressure to them. You can fire these air guns about 5,000 psi. And a little bit of video here, when you like this one, will also play, but you can see some of these air guns firing up toward the module. So air guns here, this is the float, there's actually water surface here, you see reflections, but you get the pressure pulse from the air gun, and then you get the water that's pushed out ahead of the air gun bubble that's coming out. And it's those two mechanisms that effectively, what that's doing is, like an explosive charge, all an explosive charge is doing the shock load is exciting natural response frequencies of a ship, and that's what the air guns do too. One issue with the air guns is they don't quite excite all the very high natural frequency responses you get with an explosive charge. But that's one thing. So just to finish up with, just to show you an air gun shock loading of platform. So back in 2008, the UK MOD, Ministry of Defence, shock loaded one of the old Type 42 destroyers. And I should point out Weidlinger, or now called Tomasetti in the UK, they're the companies developing this technique. And if we do an Australian shock trial, we'll have them over here running part of the trial for us. But basically, so this is ex-HMS Cardiff here. This is a 16 air gun shock trial firing these air guns at 3,000 psi. So here are is the air gun array, or when you have more than one module, they'll call them arrays. So 16 air guns against here. The thing to note is that the air guns are right up against the hull of the platform. And to achieve that shock loading effect, you've got to have a fair bit of pressure in there. The only disadvantage in this case of the air guns is that if you get too close, they may dent the whole plating, but also they produce very high displacements, and you'll see a lot of whipping and structural response on this platform when it's shock loaded, assuming it's video. And watch for the air that comes up to the surface around the module when they fire. I'm not quite sure if carpet filling bag was required or not. But you know, it's an ideal situation to do a hull whipping test on the platform also. Okay, so last slide, I guess potentially we're looking to run a future ran shock trial with air guns in the future, because it's unlikely we're going to get permission to fire explosive charges in the water again. But basically we'll be working with Fulton Thomas City, the UK Ministry of Defence, and also Canadian Department of Defence. Canadians actually did a shock trial on one of their frigates a couple of years ago now, but this was towards the end of its life. There's going to be an opportunity to test the platform dockside, or potentially we could also test in a flooded dry dock. And if we do it in a flooded dry dock, that takes away all the environmental considerations we have to worry about. May or may not have a crew present, only a 2-week test period. If you did an explosive test, it may go on for months, as you bring the platform backwards and forwards. You might only do one explosive charge a week. With the air guns, you can fire them every 10 seconds if you want to. And I guess most importantly, we could use the structural response map of that platform. With that structural response map, I mean, you can't load at full design level of what that platform will survive in shock loading. But we then use modelling and simulation to sort of scale up those responses and then do a comparison with how equipment's likely to perform in that situation. So that's my last slide. Apologies for one video that didn't work. I mean, the torrents, as I think Stephen said, I think it's online potentially on YouTube. Possibly. So look up HMS torrents, but in that video you'll see all those elements of the shock loading. So I think I might have taken more of my time than I should have, so I'll open the floor to any questions. Stunned silence now.
Have you done any audits on like Navy ships to see how many things are actually shock mounted and come to?
Yes, so when they produce a naval ship for the first time, and typically this will be done by a Naval Technical Bureau up in Canberra. They'll do an audit of the whole platform in terms of looking how equipment's mounted, where it's got shock isolation mounts. One of the things that usually causes equipment to fail, for instance, could be cabling runs in the back of equipment. You get a lot of movement in equipment and those cables could get pulled out. Water pipes running from deck to deck. Often decks will move apart and can rip water pipes apart. So an audit will be done of the platform, which we stand here, before that ship gets the OK of being accepted into the Navy. Sorry. Yeah.
In testing, you found a correlation between the accelerations experienced on the platform, on the equipment, and what is in standards. The other reason I ask that is because in our day-to-day work, we've got a lot of shock qualification problems to solve, and I'm actually just curious to know that realistic.
Yeah, look, one of the big problems is that you could have two items of equipment in the same compartment, and depending where it's mounted, its behaviour could be vastly different. So if it's mounted near a bulkhead, you'll get a very short, sharp acceleration response. If it's in the middle of the deck in the compartment, the acceleration might be an order of magnitude less. So I guess the shock standards typically will break the ship up into a number of sections and say, okay, this equipment is mounted in section 2 or 3, therefore the shock requirement is usually an estimate of what it's going to survive. One advantage of using numerical modelling, and this is where I point to Stephen Candia at this point, is that with the numerical modelling, technically you can load a platform up with an explosive charge, load the model up, and it should tell you exactly in every location throughout the ship that particular equipment of a certain mass there, how do we respond acceleration-wise? What we do find is the velocities are always the same throughout the ship, but its accelerations are really hard to predict, and it's how it's mounted is important. But one of the hopes with numerical modelling in the future is that you'll have your full CAD model there, you can load it up with an explosive loading scenario, and it will say, yep, that equipment in that location will see 557 Gs. And if you've only tested it to 500 Gs in the laboratory, you go, that could fail on the ship. You may have to re-shock test it in the laboratory. So that's one of the big things we're trying to push in terms of numerical. But all those standards and other information, I guess, shock requirements, they're usually just estimates based on past experience. So that's one of the issues we have at the moment, but that's why we're pushing numerical modelling.
Essentially validating what's already published, or in fact revising it depending on.
So in the future, the ideal situation will be, they'll say, we want to take this platform into somewhere in the rest of the world where things may happen to it, mine goes off. They'll say, what mine might it encounter, what standoff distance, you feed that into your model, you load it up with the shock wave, and it says, oh, that system's going to drop out, that one's going to drop out.
You'll be able to tell whether your platform's stonefish proof or...
Yeah, I mean, all very good in theory. As Stephen will tell you, it's in practice where it's, we're not going to probably achieve this in the next few years, but with the advent of supercomputing, we can produce a full final model of the platform. How long it would take to run, I don't know.
So basically we're more looking at the next generation of naval platforms having that kind of information.
Well, yeah, and I mentioned about...
Certainly not the current generation.
Look, I mentioned one of the earlier slides, I mentioned LS Dyna, full numerical model, I mentioned Trident. Potentially Trident is what we're looking at, is where we might be able to do, well, certainly zero in much more accurately than what we do at the moment with just having full shock regions. Trident will hopefully tell us, generally in certain regions, that equipment won't survive that particular location.
So thank you very much. I'm also very interested in the new shock testing facility. I might have a chat to you online.
Okay, yeah, sure. I was going to say, I don't know where I should say, DST is having an industry or a partnership week, a couple of days in August. There's potentially opportunity to learn more about that, whether you may or may get invited to the Partnerships Week, but we can fill you in more of those opportunities.
Sorry, a lot of the shock standards are focused on equipment vulnerability.
Mm-hmm.
How about like the design of the ship structure? Where is that covered?
Yeah, look, in the past, because the structure was generally very much more resistant than the equipment, we didn't tend to worry about it.
Yeah.
I guess over the past 30, 40 years, ship structures are getting lighter, more commercial-like.
That's right.
We do have a lot more concerns about the performance of the structure now.
Yeah.
And the onset of inelastic deformation and things like that.
Yeah.
So that's, in the past we probably wouldn't have done much work in terms of structural vulnerability.
Yeah.
But now we're beginning to look at a lot more of that. Some standards do have that. For instance, in the Australian standard, we've now incorporated a hull whipping requirement.
Yeah. You mean
and the US now, rather than just doing big explosive charge, they'll do a shot with one small charge to try and look at hull whipping on the platform. If that's going to be an issue.
Okay.
So yeah, and look, we're looking at updating the Australian standard at the moment to take into account more of that structural vulnerability side of things. So, but yes, it is a worry. Ships are getting, compared with World War II, ship structures are getting lighter. And potentially more susceptible to damage.
Yeah. So with the reprint assessment that you mentioned, what would be the acceptance criteria generally for a reprint assessment?
So I can't talk any actual figures, but we expect the hull structure to survive more than the equipment, generally a lot more.
Okay.
That may or may not be the case for some platforms. A lot more.
That's what I think as well.
So we're becoming more and more aware of that, and that's why that structural vulnerability work program, we're looking at performance of the steels, high strain rate properties, what happens if we do get a close charge, which may not take out equipment, but may damage the structure. Yep.
With this research and analysis that you're doing, the tools that you're building, how do you envision that being brought to the existing housing? To really work with designers?
So I guess for some of the tools we have, potentially, you might want to correct me, Zenka, but for DST, we're aiming to develop those tools and potentially throw them over the fence to whoever. Now, whoever at this stage is probably more likely to be Naval Technical Bureau, who's responsible for the requirements for the naval platforms, but I can imagine in the future, and look, there is already software out there that people can utilise, so LS Dyna, you can buy that from the US, although the USA code, which is a fluid structure interaction module of it, you need to get permission from the US government to buy that. Generally only, I guess foreign governments may only be able to have that, but you can buy US Dyna now and do a run a shock evaluation. Now, having said that, the old problem of rubbish in and rubbish out. Results happens, and we've got guys who are running the software at the moment, 30 years experience in the shock loading area, and at the moment we still may not match up some of those results. So this is all work in progress at the moment. What some of the other codes, and I don't know whether there's plans for UVAN to potentially go out there, but we're working on simpler tools that could be utilised by people out there working in the defence industry, for instance, who might be able to run a scenario and say, your platform may not survive this particular shock load, therefore I need to look at some other aspects of the equipment performance. And I guess some of those tools may become available in the next few years, rather than just going to a simple shock standard. It says it needs to survive this shock pulse. Test it that. If it survives, tick. We're hoping to zero in and have that process, I guess, more accurately presented and discussed, available to people, I suppose. But yeah, that's something we need to think more about, I guess. But anyone can buy those codes, but be aware they're pretty complicated to run, and you need to know your shockwave physics to get the right result out of them. I guess that's the major caveat.
Yeah.
to add.
Yeah, getting that initial information might be.
And look,
quite
we've done some recent trials on submerged cylinders. That's all I can say. We're getting some pretty reasonable results out of the matching up the shock response. Now, be aware that I don't want to say there's a fair bit of fiddling, but there's a fair bit of reassessment and validation of that to make sure they're working. We're still not quite there, but we're getting there in terms of some of these codes. But the concern is those codes are readily available, and I think some people are just readily running them at the moment, just taking the first result they get. I can guarantee that if you haven't had much experience in the area, you probably won't get the right result. So, question over.
Sorry, I've got one more. Just now you mentioned about you guys have done a fair bit of testing of material in the high strain rates, and generally, what do you see as the trend when the behavior for steels?
So generally, as you move up in the high strain rates, so the elastic range, the steel elastic modulus will stay the same, but yield points will move higher.
Yep.
UTS's probably be a little bit higher. Elongation of fracture may be lower.
Oh, okay.
That's generally one of the things we notice, especially with that DH and EH grade steel. So the processing of the material becomes very important.
Yeah.
But a lot of materials that have high yield points and high yield strengths and high UTSs, long elongations of fracture, can perform very badly in a high strain rate situation. And a lot of that's due to the impurities in there. At high strain rates, the performance can change quite dramatically. Adiabatic shear forming, so localised heating, failure across those adiabatic shear bands, for instance. But it does vary from steel to steel. And you could have the same steel grade, but it could vary from batch to batch depending on how clean the steel is. So one thing we're realising is that the cleaner you can make that steel,
The better.
and the less cleaner it is, the better it will perform, most certainly. And that's why we're looking at, with the steel manufacturer, Prime Minister has said our next ships will probably be made from Australian steel. We're looking to try and control the cleanliness of that steel, and ultimately that will make a huge difference to the performance of the platform.
Yeah.
We think.
Yeah.
So,
The only problem, we might not be able to source the Holland profiles in Australia.
sorry,
We might not be able to source the Holland profiles.
Oh, okay, yes.
Yeah, in Australia.
So yeah, look for an E-grade steel.
Yeah.
And whether it comes down to a combination of E, D-grade steels.
Yeah.
Look, we're expecting next platform will probably be made from D-grade steel, but we're looking to build up a case and maybe have sections of it made from an E-grade steel.
Yeah.
There's no welding difference between E and D-grade steel, but as you say, there are certain profiles may not be available.
That's right.
But it might just be whole plating.
Yeah.
Is from an E-grade steel.
Yeah.
We'll have to wait and see. Will I take up too much time, Siobhan? Probably.
One more.
Oh, one. Oh,
Yeah.
sorry. Quick one, or afterwards maybe.
Yeah, thank you. How this would behave in aluminium? Any idea?
Sorry, for high strain rate performance.
Yeah.
So generally for aluminium, high strain rate performance decreases. So aluminium, like titanium, is very susceptible to adiabatic shear band formation. So generally, although some aluminiums can soften from quasi-static strain rates to slightly higher strain rates, they can soften and be worse, but they then can improve. Just depends on what type of aluminium element. Ask me about it. So 5083, for instance, I think that can drop. Its properties can drop a little bit, and then it will improve again as you go to much higher strain rates. That's going from memory, I think. But there's a lot of information out there, but be aware that standard information will be just for a particular batch. If you had the same batch made by someone else, it could have different properties again. So, okay.
Hey, good for joining me, and thank you. And thanks everyone for your patience with the technical glitches.
Well, there's only one video that didn't work,
Yeah,
so I
sorry
suppose.
about the video, but feel free to get out your phones and do your HMS Torrents torpedoes with video, so I recommend it.
Yeah, on the other laptop, I think I've got the actual video